Okay, here I've got water behind a dam. This is liquid water. It comes in at this pressure and velocity, throws through the turbine, exits 300 feet below with that pressure, velocity, temperature. We've got some diameters. We know the acceleration is 32.2. I know that I can get 8 cents per kilowatt hour for my electricity. I want to figure out how much money per day I can make for steady state operation. Okay, so this is a reversible, steady state flow of an incompressible substance. Because of that, the work or the power I can create is the mass flow times the volume times a change in pressure. And again, this is because it is incompressible. Volume is constant because it's a liquid water. And now this one, the kinetic and potential energy effects cannot be ignored. So that'll be plus V1 squared minus V2 squared. That is the velocity or the kinetic energy plus G times the change in elevation, Z1 minus Z2. Okay, so the first thing I'm going to do is calculate my mass flow here. Okay, and my mass flow again is given as AV over V, right? Where V, okay, I'll start at well, that's going to be for either one, honestly. Okay, so I will go to, let me see here, 50 degrees Fahrenheit. Okay, this is liquid water, so I don't have tables for it at these pressures. So I'm actually going to use saturated liquid. Oops, I got to use the English tables. So I use saturated liquid at 50 degrees Fahrenheit. So that's table A2. Here's my saturated liquid, 50 degrees Fahrenheit, and you can see that my volume is 0.01602, and that's cubic feet per pound. Okay, so that's 0.01602, that's cubic feet per pound. So to do this, I have my area, which is pi over 4d squared, where d is given as 4 feet. Is it not? Double check. Yes. So pi over 4d squared, okay, times down here, I'm doing the exit, 35 feet per second. Again, that's because I have the diameter of the exit pipe, I have the temperature at the exit pipe, although the velocity, or excuse me, the volume remains constant. The velocity definitely changes. Okay. Now my units here are going to work out because I have cubic feet per second up here. I have cubic feet per pound, so I'm going to have pounds per second here for my mass flow, and I get 27,455 pounds per second. That's my mass flow. Okay, so here's the thing now. Now I know my mass flow, I know my volume, my pressures are given, my volumes are given, my gravity is given, my change in elevation is given. So now it's just a matter of plugging in these numbers to find the work. And there's some unit conversions we have to do. So again, my mass flow is 27455, and that is pounds per second, times 0.01602 times the pressure change, which 16 minus 14.7. Of course, that's in pounds per square inch, so I need to convert that to pounds per square feet. So there's 144 square inches in every square foot. Okay, plus the velocity squared difference, which is going to be 4 squared minus 35 squared. These are feet squared per second squared. Okay, I will refer you to the book to find this relationship, but I use that gravity, which is going to be pounds force per pound mass, or pounds force feet per second squared equals a pound mass. What this does is it puts everything in foot pounds for me, which is what I'm ultimately looking for. Okay, plus, again, my gravity, which is 32.2 times 300. And again, that's going to also be feet squared per second squared, because this is feet per second squared. This is feet, so feet squared per second squared. So I have to divide this one as well by 32.2 in order to get foot-pounds per pound mass. And again, we've done that before. So now I have foot-pounds per pound mass. I want to get this in BTUs. So what I do here is I divide this by 778. To get this into BTUs, that would actually be BTUs per second. And then I need to take that to get this into kilowatt hours, right? Because right now this is in BTUs per second. Okay. I take it times 3,600 seconds, because that's how many seconds are in an hour, and I divide it by the conversion factor to go from BTUs per hour to kilowatts, and I get a work of 10,570 kilowatts. Now I know those conversion factors are confusing. This again goes from PSI to pounds per square foot. These are converting from feet squared per second squared to foot-pounds per pound mass. We've done that one before using that relationship between foot-pounds and pound mass. Pound mass and foot-pounds per second squared. That's what it is. This goes from foot-pounds to BTUs, and this one goes from BTUs per hour to kilowatts to get me into kilowatts. Okay. Then I take that kilowatts times 24 hours to find out how many I have in a day times 8 cents per kilowatt hour, and this will give me $20,294 per day. Now, a lot of that is unit conversions that we've done before. Okay. Hopefully you followed along with those. I would move you to the book if something didn't make sense on those conversion factors. Okay. But the new stuff here is recognizing that I have steady state incompressible flow. So my work here is given by this equation here, where it's VdP, and then kinetic and potential energy effects, and then a whole bunch of conversion factors to go from foot-pounds into kilowatts and get it ultimately into dollars per day.